Good morning, good afternoon, good evening. This is video number 9 of STAT 248, Couplings and Monte Carlo. We are covering the material associated with chapter 4, which is couplings of Markov chains in order to obtain convergence diagnostics for MCMC, and also to, in this video, we'll see techniques to remove the bias of MCMC algorithms using pairs of chains with a lag. So previously in the course, we looked at couplings of Markov chains, denoted by xt and yt, and the couplings were such that there existed a meeting time, which means an integer-valued random variable, assumed to be finite with probability 1, such that at all times after the meeting time tau, xt would be equal to yt exactly. And those couplings are useful for a variety of reasons. In theoretical studies, we assume that yt is a stationary Markov chain. So it is such that yt follows pi, the target distribution, at all times t. And those couplings are then used to obtain geometric ergodicity result for the Markov chain xt of interest. We've also looked in the previous video at the diagnostics of convergence from Val Johnson's work in 1996 using C chains, so more than two chains, a number C of chains that are coupled in such a way that they all meet eventually. And that resulted in a diagnostic of convergence assuming some closeness between the target distribution pi and the initial distribution pi 0. Namely, we assume that a rejection sampler from pi 0 to pi would accept sometimes a draw from pi with some non-negligible probability. Today, we look at methods that are based on couplings, but with a lag. So we'll talk about lagged chains. And so, to be precise, here is the construction of the two chains under consideration in this video. x0, y0 are both from pi 0, for example, independently from pi 0. Then x1 is sampled from k, given x0. And after that, xt plus 1 and yt are sampled from a coupled Markov kernel k bar using xt and yt minus 1. So the next pair is sampled given the previous pair, but with this lag between x and t, between x and y. The construction is such that xt follows pi t, and yt also follows pi t. So at each time, xt and yt have the same distribution. However, there will exist a meeting time such that xt will be equal to yt minus 1, almost surely for all times after the meeting time. So we both have equality in distribution at time t and equality almost sure after the meeting time with a lag. So first, it is possible indeed to construct such chains. And in chapter 4, there are some examples of constructions. In this video, we will assume that we can construct those chains, and we will look at the use of those coupled chains in the construction of unbiased estimators, and also to obtain convergence diagnostics that are alternative diagnostics, very similar to the ones of Val and Johnson, but slightly different. In particular, there will be no assumption, no restrictive assumption on the initial distribution pi 0. We will not assume that it is close to pi in any way. So let us first look at the construction of unbiased estimators. So by unbiased estimators, we mean random variables that have expectation equal to the quantity of interest, which here refers to the expectation under the target distribution pi of h of x, where h is a function of interest and x is the random variable distributed according to pi. So in integral, this is the integral of h of x, pi of x dx, or pi of dx. So let's look at this construction of unbiased estimation. We write the quantity of interest as a limit when time t goes to infinity of the expectation of h of xt, the Markov chain at step t. And any limit can be written as a telescopic sum started from any arbitrary index k, where we have expectation of h of xk plus the next expectation minus expectation of h of xk plus the expectation after that minus the previous one, and so on. And so we can rewrite this as the expectation of h of xk, the Markov chain at step k, plus the infinite sum from k plus 1 to infinity of the difference between the expectation of h of xt minus the expectation of h of yt minus 1. So instead of an xt minus 1 here, we write yt minus 1. And we can do that because at all times t, xt has the same distribution as yt, and that's denoted by pi t. In other words, for any function h, the expectation of h of xt minus 1 is equal to the expectation of h of yt minus 1. So we have this infinite sum of differences of expectation. And next, we will assume that we can swap the expectation and the infinite limit in the infinite sum. So we swap the expectation and the limit to obtain that the quantity of interest, the expectation of h of x under pi, is the expectation of h of xk plus the infinite sum of differences between xt and yt minus 1, h of xt minus h of yt minus 1 for all times after k plus 1. And so the variable inside the expectation is the unbiased estimator under consideration. And it looks a bit daunting because of the infinite sum, but because the chains meet with a lag, the infinite sum is in fact equal to a sum up to the meeting time. That's because xt equal yt minus 1 for all times t from the meeting time onward. And the whole reasoning above works for all integers k. So we write this estimator capital HK, and we could have chosen any k, 0, 1, or any number. We will discuss later on the choice of the integer k. So it's a tuning parameter for the user. Note also that in the expression of the estimator, we have a sum from k plus 1 to tau minus 1, but k plus 1 is fixed and tau minus 1 is a random variable. And so we set the convention that the sum is understood to be 0 if tau minus 1 is strictly less than k plus 1. So the estimator can be computed in finite time, provided that the meeting time is finite. And the cost of the estimator is more precisely the cost of tau calls to the coupled kernel k bar. That's to obtain a meeting time. And if k is chosen to be large, it's likely that tau will be less than k. So then we have to continue the chain x up to step k to obtain h of xk. So we need k minus tau calls to the kernel k, kernel big K, if little k is more than the meeting time. Now we will briefly justify that we can indeed swap the expectation and the limit, at least under some assumptions. And for this, it's convenient to introduce a simpler estimator, HKN, which is the same as hk, except that the sum runs up to little n instead of running to infinity. And it will be convenient to write the difference h of xt minus h of yt minus 1 as delta t for simplicity. So when we look at this sequence hkn as a sequence when n goes to infinity, we find that since the meeting time is almost surely finite, when n is large enough, h and k becomes identical to hk, and so certainly it converges to hk almost surely. And again, that's because the meeting time being finite, when n is larger than the meeting time, hkn is equal to hk, and so we have almost sure convergence of hkn to hk. Furthermore, we have another type of convergence for hkn. We can show that, again under some assumptions, hkn will be a Cauchy sequence in the space L2. So a Cauchy sequence in the space of random variables with finite first two moments. In other words, the random variables with finite variance. That is convenient to have this result because that implies that the limit of the sequence is in L2 and thus has also finite variance. And so to show that hkn is Cauchy, we look at the squared increments in expectation. So we consider n prime and n, with n prime larger than n. And we can compute the expectation of the square increment. It is simply the double sum over indices s and t from n plus 1 to n prime of the expectation of delta s times delta t. And that by Cauchy-Schwarz, we can upper bound each of those expectations by the square root of the expectation of delta s square times the expectation of delta t square. So that's an application of Cauchy-Schwarz inequality for all s and t's, and there's only finitely many of them. Next, we note that we can handle the expectation of delta t square by noticing that they are equal to the expectation of delta t square times the indicator that the meeting time is larger than t. Because if the meeting time is less than t, delta t is equal to 0. So next we're going to assume for simplicity that we're looking at functions h that are bounded by 1. And so we don't have any integrability issues with h. In particular, delta t square is now less than 4 almost surely. And so the expectation is less than 4 times the probability that tau is more than t, which is the expectation of the indicator. And so when we look at the squared increment, we have this upper bound in terms of 4 times a double sum over st of probability that the meeting time is more than t times probability that the meeting time is more than s, and with a square root in the sum. And now we see that this will go to 0 under some assumptions on the meeting time. In particular, if, for example, the meeting time has geometric tails, so the probability that the meeting time is more than t is less than a constant times rho to the power t, where rho is less than 1, then the sequence hkn is Cauchy in L2. In other words, under this assumption, those squared increments go to 0 when n goes to infinity, and for all n primes larger than n. And as a consequence, again, the limit is in L2, which means we can compute the expectation of the limit, which is necessarily the same as the almost sure limit. So it is hk. It's the limit of the expectation of hkn, and that we find that it is the limit of the expectation of h of xt when t goes to infinity, which is the quantity of interest. And furthermore, the variance of hk is also obtained as the limit of the variance of hkn, and we could compute an expression for it, but here we'll just notice that this is finite, again simply because Cauchy sequences converges in L2 and the limit is in L2. So, at least under some assumptions, we have the capacity to obtain an unbiased estimator of expectations with respect to pi from coupled chains that are both started from pi 0. The estimator is computable for a finite cost if the meeting time is finite, and we don't need to do any assumptions on the initial distribution pi 0. There are, on the other hand, assumptions on the coupling. So let's recall first the starting assumption, which is that the meeting time is finite, and it is such that xt is equal to yt minus 1 after the meeting. But of course, we probably want more. We probably, in practice, want the expectation of the computing time to be finite. So the expectation of the meeting time should be finite. And even geometric tails on the meeting time. That was useful in order to justify the swap. It could be relaxed to weaker assumptions, but it is certainly convenient to have this assumption, also to guarantee that we won't wait too long for the estimators to complete. So this construction is due to Peter Glynn and Chang-Han Rui in a 2014 paper, but in fact they considered a more general construction. So we'll now look briefly at what they proposed. They didn't assume that the chains would exactly meet. Instead, they assumed that the distance between the chains, again with a lag, would go to 0 as t goes to infinity in some sense, without ever necessarily meeting exactly. So we might not have xt equal to yt minus 1 ever, but the distance would go to 0 in a sense. And the estimator that they propose is slightly different, since we don't have a meeting time within another stopping criterion. So they define, let's say, zk to be the h of xk, like before, but the bias correction term now is a sum from k plus 1 to infinity of a ratio where we have the difference between xt and yt minus 1 at the numerator, like before, times an indicator that t is less than a random variable n, and we divide this term by the probability that t is less than this random variable n, where this n is called the truncation variable, and it is an integer valued random variable assumed independent of xt and yt, so independent of everything else. For example, you can think of it as a geometric random variable, or Poisson random variable. So n, with this construction, will have to be well chosen for the variance of this estimator zk to be finite. In fact, some calculations will show that the distribution that n must satisfy has to be chosen in relation to the contraction between the chains. You can see lots of interesting remarks in Agapiu, Roberts and Vollmer 2018 for the application of such estimators in the context of MCMC and on the choice of this truncation random variable n. So let's have another look at our estimator, our unbiased estimator from the chains that meet exactly this time, hk. So it's made of the function h evaluated at xk plus a bias correction term, which is an infinite sum with only finitely many non-zero terms. So natural question is, how do we choose the integer k, the tuning parameter k? Well, the bias is 0 for any choice of k. On the other hand, the variance will depend on k. In fact, it will tend to decrease with k. And the cost is random because it depends on the meeting time, but it also depends on k, and it will tend to increase with k. And so in order to decide, it's good to recall some notions of efficiencies for estimators. If we look at the central limit theorem for independent copies of this estimator, denoted by hk1 to hk capital R, right? So we imagine that we perform R times the calculations. We run R times the pairs of chains such that they meet. And then we obtain a central limit theorem for the average over the R repetitions of the estimator. So the convergence is towards the expectation of interest when big R goes to infinity. And we have a distributional limit that is a normal with variance Vk. That's the asymptotic variance in the CLT, or in this case, that's simply the variance of Hk. And so a convenient notion to understand the choice of k is to think in terms of inefficiency, which is defined as the variance times the expected cost. That takes into account the fact that if an estimator is more expensive, we expect it to have a smaller variance for it to be still competitive. So the cost here, again, is going to be counted as the number of calls to the coupled kernel k bar plus the number of calls to the kernel k. So if we count the cost of k bar as twice the cost of k in units of calls to the transition kernel capital K, then the cost of the estimator is 2 times tau plus the maximum between 0 and k minus tau. So that's the cost, very explicit formula of the cost. And the variance, on the other hand, we won't have an explicit formula, but we will be able to estimate it from pilot runs. And this is to be compared with the MCMC inefficiency, which is VMCMC, an asymptotic variance, normalized by, the unit being a single call to the Markov transition kernel K. So then we have a CLT for the MCMC estimate with an asymptotic variance VMCMC. What is this asymptotic variance? Is itself can be written in various ways. For example, it's the variance of h of x under pi plus twice the infinite sum of covariances between h of x0 and h of xt when t is larger than 1. And because of this infinite sum of covariances, it is not easy to estimate the asymptotic variance of MCMC, and there's a vast literature on it. There are various packages in Python and R to implement those estimates. But recall that it is just not trivial to estimate this asymptotic variance, whereas Vk is simple to estimate with this standard empirical variance estimate. So let's look in more details at the cost and the variance of the estimate, hk, as a function of little k. So we talked about the expected cost. Let's look at how it might be represented as a function of k. K could be any integer larger or equal to 0. And on the y-axis here we plot the expected cost. And so when k is 0, the cost is the expectation of 2 tau. And when k grows, this will tend to grow eventually proportionally to k. When k is very large, tau will be typically negligible in front of k, and so the cost increases then linearly with k. Next, let's have a look at the variance as a function of k. I'll recall the estimate is h of xk plus the bias correction term, which is a sum of differences between the two chains, the function evaluated at the two chains with a lag. So that's what we call the bias correction term. And note that when k is large compared to the typical values of tau, again, tau is random, but k is fixed. So if tau happens to be smaller than k, or in fact smaller than k plus 2, the bias correction term is equal to 0 exactly. And so we will be 0 with high probability if k is a large quantile of the distribution of tau. So if the probability that tau is less than k is itself close to 1, meaning k is a large quantile of the distribution of tau. And in that case, if k is large, the variance of the estimator is similar to the variance of h of xk. So we can visualize the variance as a function of k, and it will tend to decrease initially when k increases, but only to a certain level, and asymptotically in k it becomes the variance of h of x under pi, because h of xk behaves like h of x under pi when k is large. So what we want to do is factor in both the variance and the cost when we choose k. So the variance decreases, the cost increases, and we are interested in minimizing the product. And so we have a trade-off. Typically the optimal k will be somewhere in the middle. It will practically never be 0. And we can approximate both the expected cost and the variance using preliminary runs. And that is very convenient, of course, thanks to the unbiased estimation property, the unbiased property that we don't have to worry about the bias, which we could not estimate. So here, all the quantities involved, variance and cost, can be estimated from IID replicates of the estimator. Next, we discuss how unbiased estimators lead to convergence diagnostics for MCMC. And by convergence diagnostics, we refer to concrete bounds on the distance to stationarity of the Markov chain at time t. And so we will look first at total variation, and the total variation distance between pi t and pi as a supremum over all bounded functions h of the difference between the expectation of h of xt and the expectation under pi. That's over all functions h with absolute value of h of x less than 1 for all x. And this inside the absolute values is in fact exactly the expectation of the bias correction term. And so we can write expectation of the sum from s going from t plus 1 to tau minus 1 of the difference between the function h evaluated at xs and ys minus 1. And if we consider functions h that are bounded by 1, then for all x, y, the difference between h of x and h of y is bounded by 2, which means that we can upper bound almost surely the bias correction term. So the sum of the differences between the functions from time s equal to t plus 1 to tau minus 1, that is less than if we summed the number 2 at every term, because the function evaluations differences are less than 2. And that simply is the number of terms in the sum times 2. The number of terms is the maximum between 0 and tau minus t minus 1. And therefore, we obtain an upper bound on the total variation distance between pi t and pi in the form of an expectation of the maximum between 0 and tau minus t minus 1. I should have written above 1/2 in front of the supremum in the definition of the TV. So the 1/2 cancels out with the times 2. We can visualize this upper bound. So if we have the time as an x-axis and the total variation distance on the y-axis, it should be between 0 and 1. And so we can plot, for example, a typical trace of the total variation distance, and in dashed lines we would have our expectation here. So that's an expectation which we cannot analytically compute, but using R independent meeting times, tau 1 to tau capital R, obtained by sampling the coupled chains until they meet, we can approximate the expectation by an average 1 over capital R of the sum of the maximum between 0 and the observed tau minus t minus 1. And so, of course, as the number of independent replications goes to infinity, we will consistently estimate the expectation. We can also obtain upper bounds on other distances. For example, the 1 Wasserstein distance can be upper bounded similarly, with a similar reasoning, by the expectation of the sum from t plus 1 to tau minus 1 of the difference, the distance between xs and ys minus 1. We can obtain this upper bound using the representation of the Wasserstein 1 distance as a supremum over the 1 Lipschitz functions. So that is the functions h that are Lipschitz with Lipschitz coefficient less than 1. And we can then upper bound the difference between function evaluations by the distance between x and y. So from the unbiased estimators, we obtain convergence diagnostics, and again, the specificity of those diagnostics compared to Wallen-Johnson's diagnostics is that there are no assumptions on the initial distribution. So we might start very far away from stationarity and still obtain concrete bounds on the distance to stationarity. The same reasoning holds for any lag. So the previous slides show the reasoning carried out with a lag equal to 1, but we could do the same reasoning with a lag L larger than 1. And in a nutshell, it relies on the same telescopic sum decomposition, but started from index k, but doing steps of size L instead of steps of size 1. So we have the expectation at times k plus L, k plus 2L, and so on and so forth. And so the unbiased estimator that we can obtain with a lag L starting from index k is, we can write it hk again. It's the function h evaluated at xk, and then we can sum over integers j larger than 1 the difference between xt plus jl and yt plus j minus 1l. So we do the same reasoning with steps of size L instead of steps of size 1. And of course, then L becomes a tuning parameter, so we have to choose it. We could choose 1 as before, but it might be interesting, for example, in terms of efficiency of the estimators, to increase the lag. So just to be clear, if we have a lag larger than 1, the initialization of the chains goes as follows. You still start from pi 0. This should be pi 0 and not pi. And then you propagate the x chain for L steps. So you create x1 given x0 from k, xl given xl minus 1 from k, given xl minus 1. And then from step L, you start coupling. So you generate xt plus 1 yt minus L plus 1 given xt yt minus L from the coupled kernel k bar. So it's the same construction than with the lag 1, except L can be any integer. So we basically advance the x chain for L steps. We have xl and y0, and then we start generating xl plus 1 y1, xl plus 2 y2, and so forth, recursively using the Markov kernel k bar. So when we employ such couplings with a lag of L, the diagnostics of convergence follows the same reasoning, and we obtain that the TV between pi t and pi becomes the expectation of the max between 0 and the ceiling function applied to the ratio tau minus L minus t over L. The ceiling function applies to the ratio, in fact. The ceiling function is the integer above the number in the argument. And one thing that is appealing in this expression compared to when we had a lag of 1 is that as the lag goes to infinity, as it increases, the upper bound here goes to 1, to something at most 1, which is appealing because the TV on the left is always between 0 and 1. And so it's a very clear way of seeing that increasing the lag provides sharper results, more precise results. You can hear more or read more about the choice of lag, which still has a lot of open questions about it, in a paper by Niloy Biswas, myself, and Paul Vanetti, and also a comment by Paul Vanetti and Arnaud Doucet in a 2020 discussion paper. So next we'll go back to the efficiency or inefficiency of the proposed unbiased estimator, HK, which we write again h of xk plus the infinite sum of deltas, where delta t is h of xt minus h of yt minus 1, or t minus l if we employed another lag. And we're interested in the efficiency or lack of efficiency relative to MCMC. So what is the cost of debiasing relative to standard MCMC? And we noted already that if k is large, little k, the index chosen by the user, then the estimator is equal to h of xk with large probability. And this points at a clear lack of efficiency of the proposed procedure. So namely, the proposed procedure requires the generation of the x chain up to step k. So we have to generate x0, x1 to step xk, and perhaps even more steps if the meeting time occurs later, but at least we need to generate k steps. But the estimate only employs the last state xk. So all the other ones are thrown away in the final estimator. And that seems sort of apparently wasteful. And indeed it is wasteful. And we compare to standard MCMC. In standard MCMC, we generate, say, capital T steps using our Markov kernel, and we employ all the steps in our final estimate, at least all the steps post burn-in, so after the initial discard of some steps, we employ all the subsequent steps. We don't use only the very last step. And so indeed, it's much more efficient to arrive close to stationarity and then to exploit the chain there. And we can do that also by maintaining the unbiased property. And so the improved estimator, the next estimator, is obtained by averaging hk for different values of k. It's written hk colon m, and it's simply defined as the average of hl for L going from k to little m. And just to be clear, we consider averaging those estimates constructed from the same coupled chain, from the same trajectories. So what we do is we run the coupled trajectories as if we employed little m as the tuning parameter, but from that we can exploit the intermediate steps from k to m, and we still have to choose now parameters k and m. So by averaging unbiased estimators, we obtain still an unbiased estimator. So the expectation is unchanged. It's the quantity of interest. And we can rearrange the proposed estimator by writing the different HL as follows. So HK is H of xk plus delta k plus 1 plus delta k plus 2 plus delta k plus 3 and so on and so forth. Of course, those deltas eventually are going to be zeros, but we can imagine that they're all there. And write hk plus 1. And we align the terms according to the time index. So we put the delta k plus 2s underneath one another, and then delta k plus 3s, and so on. and I'm going to just write one more, hk plus 2. This one is h of xk plus 2 plus delta k plus 3 plus delta k plus 4, and so on and so forth. And so if we average those estimators and rearrange the terms, we find that h of hk colon m can be written as the average from L equal k to m of hkl, so simply the evaluations of the function at the Markov chain. So we have a term like this, which looks a lot like an MCMC average. And then we collect the bias correction terms by deltas together. And we find that this becomes a sum weighted, because the deltas appear multiple times. So we have this minimum of m minus k plus 1 t minus k times delta t. And when we see this form of the estimator, we see that the estimator is made of a part that is exactly like the standard MCMC estimate, as if we employed a burn-in of size k, or k minus 1, and a total period of length m. And we have next to it the bias correction term. And this form is much more appealing than the previous estimator hk, because now we see that the efficiency of the estimator might be related to the original efficiency of MCMC, at least if k and m are large enough. We conclude this video by noting that instead of having those functions h appearing in all the formulas, we could get rid of the functions h and consider the approximations obtained with lag chains as procedures that deliver probability measures, or as we'll see, sign measures. So we can consider the approximation without thinking in advance of a specific function h. And indeed, when we generate the chains on the computer, we don't need to specify a function h. So if we look at standard MCMC in that way, we see that it's as if it generates an empirical measure with a delta mass at each of the xt's in the chain after burn-in. So here it's written as if there was a burn-in of length b and a total length capital T. And so we can imagine the state space, and the x's are on the state space, x7, x31, all the x's are there, associated with a little mass equal to 1 over the period of the trajectory under consideration. So they all have the same mass. They should have all the same vertical stick here. And if we look at unbiased MCMC now, just recopying the previous formula but without the h's, instead delta masses at the x's and at the y's, we have, well, the MCMC empirical probability distribution, and then we have a sum of differences between delta masses. So we have a delta mass with a positive weight for xt and a negative weight for yt minus 1. And the mass is different, depends on t, k, and m here. And so if we can think of this as locations on the state space again, some of them have a mass exactly equal to 1 over m minus k plus 1. That's coming from the MCMC part. But we also have some points associated with different masses, positive and negative. So the negative ones come from the y's, and the positive ones come from the x's. And so a particular y might have a mass of minus t minus k divided by m minus k plus 1 for some t. So it's a bit peculiar. We have what's called a sign measure as a result of running the coupled chains up to their meeting time and up to step m. So there's a positive part and a negative part. And of course, if the meeting time is small compared to k, then we might have no negative atoms. But in general, we might have some negative atoms. It depends. It's a random number of negative atoms every time we run the coupled chains. And so it's not very common in the MCMC or the Monte Carlo literature that we have approximations in the form of sign measures. It doesn't affect all aspects of what we're doing with those approximations. So for example, as we've said before, we can compute averages by evaluating a function at all of the atoms. But there are practical consequences. And perhaps the most striking one, or perhaps the most annoying one, is that the resulting estimate can take values that are not in the range of the function h under consideration. So for example, if we have a function h taking values in the interval 0, 1, our estimate of the expectation of h might be, for example, negative. So we might have, for example, negative estimates of positive probabilities. Or we might have, conversely, positive estimates of quantities that we know to be negative. That's it for today. We've seen couplings of Markov chains with a lag that can result in convergence diagnostics for MCMC in the form of upper bounds on the total variation distance between the distribution of the chain at time t and the limiting distribution. And we've also seen how to remove the burn-in bias, the initialization bias from MCMC estimators. In the next and last video for this course, we'll look at couplings of Markov chains to produce perfect samples from the target distribution pi using a technique called coupling from the past.